Okay, so let us start today with Simulink. And today I'd like to show you how we can actually create some program in Simulink that will run in real time. First of all, let me explain what does it mean in real time. And I will probably start with this picture. Uh, in real time, it means that the code runs very fast, but that's not still the definition of real time. But it means that the code can run faster than it is actually required. So imagine the following situation. Let's say that I need to repeat regularly some code. For example, I will sample some values from my plant. Let's say I will measure temperature. And I know that I need to sample it with this sampling frequency. So from this time until that time, this is the sampling frequency that I require. And if I have some algorithm, this gives me this time that I have available to execute my code. So for example, I will sample here the temperature. Then I will calculate what do I need to control. So the control algorithm gets calculated here. I calculate, for example, the PID controller or some state controller or whatever. And then you output some value. So it means that before you need to sample the second input sample, you need to finish the calculation. Here we have basically what can happen. We have some time that is required to execute the model or execute our calculation. And let's say that the calculation takes this time. And then we have some spare time that we can still fill somehow. And we can fill that with some background task. For example, this could be the user interface, or it could be some other non-real-time application. So if you fulfill these conditions, that you are generating the code faster than actually required, then your code can run in real time. The other option is that it's not possible. So we can see it here on this picture. Let's say that here we have the sample that we acquire from some input. Then this is my code. And now we can see that it takes longer, and therefore this second sample will come before this it has finished. So this means that if it's this situation, now this cannot run in real time, and I need a faster hardware. Or if it's possible, I need to adjust the sampling interval, for example, to be here. So I need to decrease the sampling frequency. And now it's a question if it's possible to decrease the sampling frequency uh, if it's allowed with the process. For example, you know that you need to sample every second, and you should know if it's possible to make it like 2 second sampling time or something larger. So today we'll take a look on how to do this in Simulink. Our code, what we will have here, will be the Simulink model. And this will be the model of a plant. We will today simulate a very simple plant. We will see some transient response of this plant. And I'll show you how to make it work in real time in Simulink. we will need to install some special package for the Simulink environment, because normally Simulink does not run in real time. So real-time code is suitable for control systems where you have deterministic behavior. And determinism means that you can tell in advance what will be the sample rate of your code. So this means that in advance you are sure that you will obtain some sampling time. For example, here my sampling time that I require is from this sample to that sample. And if the code will run in real time, then it needs to keep under all conditions this sampling time. So for example, if this was time 0 and this will be time 1 second, let's say, then under all circumstances, even if I run other applications eventually, then this sampling time will be maintained. So determinism will give you a guaranteed response in time. If you run normal Simulink, and if it's not like with the real time, then this determinism is not guaranteed. So it may run very fast, but then some other parts of the operating system, they will decide to do something. For example, you are, let's say, we have more programs open at the same time. You are encoding the video, for example. You get an email and so on. And normally all those processes have very similar priority. But if you want to run a control application, the highest priority needs to be given to the control algorithm. So to sampling of the inputs, to calculation of the control action, and to the output of your data. And other stuff should be, let's say, optional when you have enough time. So the optional stuff can be the user interface, for example, or could be some data storage that you need to store your data somehow in, let's say, SD card, for example, and so on. So now in order to install the Simulink real-time, it's called a kernel, then we need to perform some actions in MATLAB. So now I will start MATLAB, and I will show you how we can actually start the coding. I already have the Simulink started, so I'll just start from scratch. And you need to perform this command in MATLAB, and this command will install you the Simulink real-time kernel. Now we will need this kernel a little bit later during the first project and the second project as well, because the whole point of this simulation in Simulink would be that we will make the plant as a model in Simulink. So this will be our simulated system, and the controller will be what we will program later for the STM board. So that's the whole point. So today we'll learn this part of the diagram. We'll learn how to make the plant model in a computer and how can it run in real time. So let's see what happens if we install this kernel. Now it will probably take some time. It's not very large, but I see some problem. It may be the reason that I don't have the same version of MATLAB as I had last time when I was trying this. So let's see. We'll have to look into the documentation, because when I was preparing this presentation, I had MATLAB 2018, or I'm not sure if it's 2018 or 19. It doesn't matter. But now I have 2020, so it's a different version, and that might be a problem. Okay, so give me a minute to find some solution, because it's possible that in this version of MATLAB it's uh, done in a different way. So I actually need to see the MATLAB forum if they have changed somehow the kernel. But no, they seem to have the same command. Aha! And now I see a problem. I did not install Simulink Desktop Real-Time. Did you install it, some of you? So I need to go back to my MATLAB installation, and I will need to install Simulink Desktop Real-Time. So if you have not installed that, please install it right now as well.
Yes, I'm installing it right now, so I need to restart my computer to be able to.
Yeah, I will do the same. So let's say we'll meet again in about, let's say, 5 minutes, and I will try to have it installed. Okay.
Okay, perfect.
Okay, so let me talk a little bit about the hardware that we should be actually using in the lab. I know that you don't have the card at home. I don't have it either. But this is to give you some brief info about the devices that we will be using in the lab. So in the lab, the computers are equipped with a card that allows us to sample the signals from some analog pins, and we can also output some output data as analog voltages. The type of the card that we are using is PCI 6024E. It's a card made by a company, National Instruments, and the card looks like this. The important point is that here we have a connector where we can actually, through a panel, connect our input signals. And this particular card has the following properties. It has 8 analog inputs. It has 2 analog outputs, and it has 8 digital inputs and 8 digital outputs. So we will be using only the analog inputs and outputs. Here we have 12 bits resolution. So within a given voltage range that the input can sample, you have 12-bit resolution. Now you can select the range of voltages that you are actually using, and this means that you can adjust the the voltage range. For example, if you have a voltage range from minus 10 volts to 10 volts, then it's always a good idea to use the full range if possible. So if you know that your signal is from 0 to 5 volts, then you should adjust the input range to use the whole resolution of the AD converter. Now, of course, sometimes it's not possible. Sometimes it may not be possible to change the range because the device does not allow it. Other devices, they may be different. They may have a fixed configuration, and then you need to go with the devices that you have available. Now, this is quite important, this number, this 200 kilosamples per second. This is the sampling frequency, and in the case of this particular device, we would need to look into the documentation if it is actually for a single channel or if it is shared for all channels together. Now, many devices are done in such a way that this sampling speed is shared between all the channels. So, for example, if you have 200 kilosamples per second and you use one channel, then you may use 200 kilosamples. But if you use two channels, then this gets divided by 2. Now, this calculation is very approximate because it also takes some time before you switch the channels. So if you switch the channels, and then it's not divided just by 2, but a little bit more than 2. Let's say 2.2, for example. We will not use this full speed because in our examples we will be actually limited by the analog output signal. For the output signal, we have two available channels, and they have the same resolution, but you can see that they have significantly smaller sampling speed. Now we will use this 1 kilosample per second in the interrupt mode. We will not use the DMA mode. Now, what does this mean? Now, the interrupt mode means that you make one sample, that this is driven by a timer that runs, and every time the timer finishes counting, it will take a sample from the AD, from the memory, and output that to the analog output. Now, this interrupt mode requires the interaction of the CPU that you have actually in your computer. So it's much slower. On the other hand, the DMA mode, DMA stands for Direct Memory Access, works in a different way. You program how many samples do you want and what sampling frequency do you want, and where should the data be stored. And then the DMA controller that runs on the card, it's programmed in one of those chips that you see on the board. Then it takes the samples and puts the samples directly to the memory of your computer, to the pre-designed space. So it has a direct access to the memory, and hence it's significantly faster. It does not require any interaction from other components in the computer. Now in Simulink, as we will run it, we will use this slower mode, the interrupt mode. We will not use the digital inputs and digital outputs. This is just to show you that they are available, and you may use them to turn on an LED, to read the state of a button, and so on. And we will see in Simulink that there are blocks that allow you to control those digital inputs and outputs. So now my MATLAB is still not finished. It says 31%. So I'll keep talking about the structure that we will be actually using. So the final goal of The whole subject that we will be doing is shown on this picture, on this block diagram. And we will try to make the hardware in the loop approach. Now this means that the plant, this is our system, will run in real time as a model on a computer. So this will be the program in the computer in Simulink. And this will be the controller that we will program into our development board. Now in this picture you see a little bit different image, it's a different board, but it doesn't matter where you actually program it. The point is that here the control algorithm runs on the hardware, and here this runs in a software. Of course, in order to transfer the signals between the plant and the controller, you will need some inputs and outputs. So here with those blocks, I want to say that you will need some signals. And those signals will be real electrical signals as in reality. And it actually depends on what plant we will model here. This could be a simple voltage that we will send from the controller to the plant. It could be also some current, because in industrial systems you probably know that we use current signals because of the higher immunity to electromagnetic interference. But this I/O might be also some data signals. So this might be USB, this might be a serial line, this might be an Ethernet connection, and so on and so on. So those signals will be the same as in reality. So for example, if my plant is some temperature control system, then this variable that I actually measure is the temperature, and I will most likely control here the electric power to a heater. Now on the other hand, if my plant is an airplane where I want to control the pitch of the airplane, now the measured signal will be the position of the airplane, and the controlled signal will be, for example, the control surfaces on the airplane, so flaps, for example. So this might be very different for every system, but this is a general block diagram where we have the connection between the control and the plant. Now, in this class, we will not be talking that much about the I/Os here. We will use simple examples, and our examples will have only one signal from the plant and to the plant. So this will be one signal, and this will be another signal. But in a real system, now you may have more variables that you need to control in a plant. Let's say you are controlling some test device, and this test device needs to control temperature and humidity at the same time. For example, you are producing some electronic circuits, and you need to verify that they work in a large temperature and humidity range. So this plant can be more complicated, and it does not have to be only a simple system where we have a single input and single output. Now about those I/Os, you will be talking in another subject that will happen in summer semester. I don't know exactly what's the name of the subject. It's something like industrial networks or something like that. Today or in this class we'll be using only voltage signals. So the input to the plant will be some voltage signal, as will be produced by this card, and the output will be again a voltage signal that will be originating from this card as well. So that's for the case when we will be in the lab. So far, we really don't know when we can have lab classes. It's changing all the time and no one can give you the answer. So what we will do is that we will work in Simulink, and we will simulate here the plant as a model. And right now we will simulate the controller as well in Simulink. And we will connect it with some signals. And after we have access to the lab, we'll replace this with the real computer with real-time Simulink. Another option that I would like to try is that we can use the controller in Simulink. Do you have some question? No, I just see that. So if you don't have any question, please mute your microphone, Mr. Messas Anis. Okay, so the possibility that I'm exploring right now is that how we can send the signals from the controller that runs in the STM board to the Simulink, and I actually have some ideas, but so far I didn't try them. So today we'll be talking about the plant, about real time, and a little bit later in the semester we'll connect the real hardware that we've been programming last time. Okay, so my MATLAB is at 65%, so it may take a few more minutes. So let me explain you how the model will look like. So our first example that we will create will be looking like this. We will have a Simulink model, and here is the input to the Simulink model. The Simulink model will run this plant model. This is a block that allows you to create a second order system, and here the output for the time being will be to a chart. So if you already have MATLAB started and you can run Simulink, then you can start creating this block diagram. Now I will leave it on screen. This is a signal generator, and I will, when my MATLAB is working again, I will show you how to build this this model. So another interrupt for a few minutes because my MATLAB is right now at 67%, and I will need a few more minutes to actually install the desktop real-time. So let me install the real-time kernel, and it should not take very long. The kernel is a special piece of software that allows you to run the model in real time. So normally this is not installed when you install Simulink by default. Now it says that I need to restart my computer. That's a great news. Okay, I will not restart right now because honestly right now I will not need the Simulink real time, because we would need Simulink real time if we would use this hardware. We can run it in real-time mode. You will see the difference, but right now on our computers it will not be any difference because we don't have the inputs and outputs from the device. So right now I will just run Simulink, and we will start creating the block diagram that you see in here. Now, do you have some experience with Simulink or not?
Yes.
Yes.
Okay, that's great. I hope that you are doing some Simulink simulations in other subjects as well. The mathematical models with Professor Lidal, for example. I know that some students don't have any experience at all with Simulink. So just a very brief introduction. The Simulink is an environment where you can drag icons, and those icons can represent parts of your model. Here, the model here that I have is a very simple model created as a transfer function. And I hope that you all know what a transfer function is from automatic control or from some other subjects. If you don't know it, you need to study it yourself. Now, if you look on this transfer function, we can see that this is actually a second order transfer function. And we could look in the roots of this characteristic equation to see if it is oscillatory. And again, I hope that you know how to do it from automatic control or from mathematics. Now, I have chosen the roots of this function in such a way that this is an oscillatory response, which you see here. So what I will do in the Simulink model is that I will create an input signal here, which will be a rectangular signal. This signal will change from 0 to 1, will last for 2.5 seconds, and then for another 2.5 seconds it will be at 0. And the reason why I have this long time in the simulation is simple. I see that the response is here, and now it gets attenuated, and here we have a steady state. So this is a transfer function, the orange one. That's the response of the system to a step on the input, so it's a transfer function. You know that the transfer function should be the response to a step size of 1, and this is the case. Here I'm changing from 0 to 1, so this is a unitary step, and then in order to repeat this as a signal continuously, here I have a rectangular wave. Now my Simulink has already started, so I can now start creating the model. So we'll first look for the transfer function itself, and you need to open the library, and let's search for the transfer function, and we will be able to drag this into the model. So this is my transfer function. Now, as you see here in this icon, it would be a first order system, and this is a continuous model. You can see that by this S variable. If you want to work directly with a discrete transfer function, you should use this block, which has 1 over z plus something. I will use continuous function, and I will just drag that to my model. And now I need to set correctly the parameters. Sometimes it's taking some time before you drag the icon to your workspace. At least on my computer right now, because I'm recording this lecture at the same time, so it may take some time before I actually am able to drag it. Let's try again. Okay, fine. So now I can have my function. If I double click the transfer function, I can now add the coefficients for the numerator and denominator. So I will keep the 1 in the numerator, and here I will create a second order transfer function which has those coefficients, so 0.005 and 0.5 and 1. Those are just some arbitrary values, but they are chosen in such a way that it's an oscillatory system. So this is my function. If I just increase the size like this, we will see the values. And now I need to look for the sources, which will be my pulse generator. So this is my pulse generator, and by double clicking I can select the properties. So I will keep the amplitude 1, but period will be 5 in my example, and pulse width will be 50, so that we have 50% on and 50% off time. And the last block that I need to use is the chart, and I will display this in a scope. And now it depends on the version of MATLAB that you have, but you can basically do also this in the newer versions of MATLAB. You can drag the wire, and now it will give you automatically the second axis. Or if you have some older version of MATLAB, you can search for something that's called a MUX multiplexer, and like this you can drag a multiplexer inside, and you can basically multiplex the signals into one, and this will display two signals. Now this really depends on your preference, if you like to do it like this with a multiplexer, or if you like to do it like I showed you, by dragging the signal directly in there. Okay, so now our model is finished. We just need to run it, and here you can see that I will run it until the time 10 seconds. For the time being, we'll keep it, but later we'll change it to some other value to run the model. So now let's just run the model. Now this will not run in real time because we didn't do the correct steps so far. And we'll see the response here in the scope. Now here you can see what is actually happening. It's compiling my libraries, and when it's finished, then here you have seen the simulation time. And now I can double click my scope, and we should be able to see the response. Okay, now it's appearing. So this is the response of my second order system. I didn't make any changes in the Simulink setting. So now you can note several things. Here on the blue curve, this should be my rectangular signal. And since I did not set any setting for the minimal time step, now you can see that this time step is quite large, and that the signal here is not very vertical. If you have a small time step, it will look like this: 0 on the input, and then ideally in a very short time, infinite time here, then it will jump to 1. So one of the settings that we need to change is to change the time step that we have in my simulation model. You can see it also here on the output signal. This does not really look like a nice oscillatory response, but it's only because of the sampling time that we have now in Simulink. So this will improve as we decrease the time step that we have for the calculation. So how to do it? We need to go back to our model, and we need to change the time step or the simulation method that this current model is using. Let's go here to the model settings in the modeling tab. And again, if you don't have the same version of MATLAB, now this may look in a different way. So what do we have in the model settings? Well, first of all, we will have the option between the solver selection with a variable step, which now by default is in Simulink, or if we want a fixed step. Now, if you are doing, let's say, normal simulations in Simulink, then the variable step might be a good option if you configure it properly. But if you are doing real-time control systems, then it should be always fixed step. If you are compiling the code in C, or if you are running it in real time, then this needs to be always fixed step. And if you now open this the details about the solver, now here you see that initially it gives us some sample time that's called auto. So it means that it will try to automatically figure out what should be the sampling time. And again, this is a thing that you need to change if you want to operate in real time, because you as the designer have to know what will be your sampling time in your application. Now there are two ways how to do it. Either you define a number directly here in the project, or you create a variable and insert this variable here at this position. So for example, you can do sample time 0.01, or let's just do 0.1, and let's see how this will be different in my simulation. So this was my variable step setting, and we don't have a fixed step size. Now if I run the simulation again, I now have a fixed step setting, and now you see that my time was probably not a good idea to have just 0.1, because here I see that okay, now I have a problem. It calculates the response at this point and at this point. So I have very few points in my data that I get. So this is telling me that actually the sampling time that I have needs to be much smaller than the speed of the system. And if you look here on this system, you see that I have well, it's not a time constant. We don't call it that in second order systems, but this smallest number is telling me something about how fast the system is. So let's try faster sampling time, and I will just change the sampling time to be 10 times smaller, so 0.01. But I know already that it's not going to be enough. Just try to see the result. It will definitely be better. So it looks like this. But if we would magnify the the chart, we would still see that there are some steps. Let me do this like that. So now, if you see here, we still have a relatively large sampling time, and the actual data point where it was calculated is here, then it's there, and then it's in here. So based on the speed of your system, you need to change the sampling time, and this needs to be related with the sampling time that is possible on your hardware. So let's say that you would like to simulate a system like that, and you know what is my sampling time that I require. And then you need to consider also if your hardware is fast enough to run this system in real time. Because I need to select the sampling time for my model and for my calculation with respect to the hardware capabilities. Here, my analog input has some sampling speed, and the analog output has also some sampling speed. So it may happen that for this particular system, this will not be good enough, and I need to look for different hardware because I need larger, faster sampling time on the output and on the input. Okay. So let's see another option how we can actually do in Simulink the setting of the sampling time. So here we had the constant sampling time in this setting. Now what we can do is that I can call this like a variable. So let's call it TS, for example. And here now this will look for a variable in MATLAB that's called TS. So far I don't have it defined, so I need to go back to MATLAB, and here I need to define the value of my variable. So let's call it TS equals to, for example, 0.001. And now this defines the variable in Simulink. Now those messages are very disturbing. Does someone know how to disable that? Actually, the messages that pop here all the time from some other meeting. I don't know how to disable it.
Maybe if you mute the team, or I don't know, mute the conversation. If it
I
is
have no idea. Now I have hidden the team. We'll see. No, it's still popping some messages from other teams, and I don't know how I can actually disable that. Doesn't matter. We'll have to live with that. Okay. So let me just play. Well, I could. No, I don't know how it's possible to do it. It's a Microsoft product. Okay, let's go back to Simulink. Now I have changed. Now I have changed this sampling time, and I can run the model. But now the sampling time will be given by the variable that we have in MATLAB. So let's run it, and we should see now right now it's actually quite fast. Now I have 1 millisecond sampling time. So now if I zoom in, you see that now we have a very good response of my system. So like this, I have figured out that the suitable sampling time for my particular system is 1 millisecond. Of course, if you would analyze this equation, you would see this from these numbers. Here, it's not exactly the time constant, but this first number is basically telling me how fast this will react. And your sampling time needs to be smaller than this number. So now we are able to run this on a computer, but right now it's not running in real time. And now comes the theoretical part only. I will show you how we would do it with the lab card that we may use sometime. Now, and I will show you also where you will find the inputs and outputs in the Simulink libraries. Now, the reason why we have actually installed Simulink real-time is that this gives us access to inputs and outputs for this particular hardware. So now if I go to the Simulink desktop real-time, I should be able to find this icon, analog input, and also this icon which would be the analog output. Now we will be able to drag them into the model, but since we don't have the card, we will not be able to run the model. That's very sad, but without lab access we will not be able to do it. So let's see what we have in the libraries. So now here I have Simulink desktop real-time, and this gives me options that I can use in my model. So now let me drag the analog input to my model, and I will also drag the analog output model, although we will not be able to use them right now. Okay, so how to configure all this? We can install, and maybe we will install it on the computers as well. But on my computer it will not work, and on yours neither, because we don't have the hardware. If now you double click on this analog input block, now so far I don't have any boards that are installed. So you need to click here, install new board. It will look for all the drivers that it actually has. And the board that we will be using in the lab is this one. It's from National Instruments. That's the manufacturer. And here is the number PCI 6024E. Now, if you require some other device, then you can look for other drivers as well. Some of them can be USB, some of them can be PCI Express, and so on. This particular device that we have is on the PCI bus. So I will just install it just to show you what will happen. But we have it installed in the lab, so when we will be in the lab, then we'll have this ready. Now in this window, we can actually configure the device. Now I will need to uncheck this, and I'm even not sure if it will install correctly, because I really don't have the card installed in my computer. Here you can see the configuration for the analog to digital converter. Let's leave it on single-ended. It means that the analog signal is ground referenced. So there is one signal, and then the second terminal is ground. In some applications, you may work also with the differential signaling, which means that you basically have two signals, and you measure the voltage difference between those two wires. Now if we would have the real card, we could use this test button to see if it's really correctly installed. I will do just OK, and now hopefully it will well, it's giving me yeah, that it cannot find the device, but if I want to use it anyway, so I will use it anyway. And now here you can see that in this list I already have my board that I would use in the lab. Here you can configure the board. Now the sampling time. Now we are talking about the timing of the hardware. So now as it is set right now, it's set to 0.1 seconds. So every 0.1 second it will read the analog input here, and it will give me the signal here on my wire in Simulink. Now what I can do, of course, is that I can set this as a variable. So this could be also the variable TS. This might be quite important as well. The maximum missed ticks. This is telling me after how many, I will say ticks right now, and I'll explain what it means later. So after how many ticks, it will give me an error that the model is not able to run as quickly as I want. Now in ticks, this is related with the speed of your computer, and MATLAB allows you to show actually the number here, how many ticks are actually missing. And since right now the model would not run in real time, then if I run my Simulink model, then it does not have total control over the PC, and Windows and other applications will interfere with it. So in the in the background, the other programs will do something. I have email running, I have the video record running, and so on and so on. So the CPU assigns some time to Simulink, and if this will miss the time window with those ticks, then it will end the Simulink code with an error saying that it did not meet the timing specifications. If we will run it later in real time, now this will be quite important because we'll need to select, let's say, a good number here. If we select it too low, then we may stop very frequently on errors. If we set it too high, it will be not a good warning if the computer is not fast enough. Now let's take a look here on the configuration of the channels. Now obviously this is the channel number. So I will pretend that now I will work with channel 1. And for this channel you can see what configuration do we actually have. And this is the voltage range that this channel can actually measure. Now obviously this will be different for different hardware. So for this particular board, the PCI 6024E, I have those 4 ranges available. So if my signal is from minus 10 volts to 10 volts, okay, great, I will select this signal. But if, for example, my signal is from 0 to 5 volts, I will select this range because it will better use the available range of the AD converter. Now here note that it's for this card it's from minus something to plus something, so it's symmetric around 0. So if my signal is just from 0 to 5 and not with the negative voltage, then what this means that I'm actually using just half of the range. But there is no way how this can be improved by this specific device. So I will keep it like this, minus 10 volts, because we will not be able to run this code anyway. Here you can select also what variable will be on the output. So default will be double, but as I showed you last week, if we will compile this Simulink code into C code, then it's actually better to select single precision, because it will run much faster on the CPU in C code. Now if I do OK, I can now connect the block here into my system, so I can remove this pulse generator, and what I can do is connect it like why isn't it not working? Let's see. Analog input like this. So I will have one input to the system, and of course I could do the same configuration here with the analog output like this, and I could also plot this into a chart. I can configure the second block again here with this PCI 6024. I could select the output range, I could select the channel, and now if we would be in the lab, now this would run on the real hardware. Unfortunately, we are not in the lab, so I have to show you only the results that we have in simulation. I've actually prepared this in advance, so this is what you would see on the oscilloscope. So now what you see here on the screen. Now this is the same response as we have the same system as we have done in simulation. Now the yellow is the input signal. It's showing just one edge of the signal, so one transition from 0 to 1. And the blue curve here is the transient response of the simulated system in Simulink. And now note those areas that I have highlighted in red here. Now you can see that here the system started to react, and here something happened. There is a step, and here something happened as well. Now in reality this might be even worse, and it's just one example that I have catch on the oscilloscope. Now what happened is that the Simulink is running now in normal mode, so it's not running in real time, and this means that we don't have any deterministic behavior in the program. So we don't have any specified time that is assigned just for Simulink. And what happened here is that some other process in the computer started to interfere. Windows started to do something, or other program, and here Simulink did not have enough time to run, and we can see this as a constant value on the output. It did not have enough time to update the actual output. And here the same. Here it was running and something happened, and suddenly it calculated a different value and started updating the value again. So what does it mean, this normal mode? You can see that here we have this setting. Here I can open this, and I can see that we have a normal mode, and we have accelerator and rapid accelerator. And so far, since I did not restart my computer, I don't have the possibility to run it in real time, which will be this external mode. For this, I will need to restart the computer and to run it again. So if you have done so, you should have all those three additional options in your Simulink. What is actually happening in Simulink is that if you run a normal simulation, it runs in an interpreted mode. So it basically runs the blocks one by one without compiling the code in advance. And if the blocks is not fast enough, then for the simulation in computer it's not a problem at all, because it can stop the time in simulation, it can wait until all the blocks are finished, and it can do another step afterwards. So sometimes if you have a very simple code, it will run faster than in real time, like it's the case here, or if it's like a really slow computer or very complicated system, it will run slower than in real time. Now we can of course accelerate the code here in MATLAB by actually compiling the Simulink code. So what I will do is that I will put back my inputs from Simulink. So the source will be the pulse generator, and I'll put it here and I'll configure it again with a period of 5 seconds and 50%. That's the pulse width. And if I run it just in the normal mode, I will run this in the interpreted mode. But if I now change to accelerator mode, what is it now doing is that it will compile this code into a max function, as we have done last week in MATLAB. And then it will run this max function. So this will be compiled and it will be faster than the normal version in Simulink. The catch here is that it needs to compile first, and that this compilation takes some time. So you can see here it was saying that compilation started, and now I am in the accelerated mode, and now the startup of the model is slower, but then the running process itself will be faster. So first of all, let's take a look on the accelerator mode. And in accelerator mode, which you need to enable in Simulink, is what is happening is that we can switch from normal mode to accelerator mode. And by default, the accelerator mode runs in something that's called just-in-time acceleration. So it means that we can compile the code in advance, and that our Simulink process like this then runs as a compiled version. What actually is happening in normal mode is shown here. You have one process. This is your model that is running in Simulink like this. So this is my model. That's my mathematical description of my system. Now here is a solver that solves the set of mathematical equations. And this whole then runs in Simulink, which maybe in a simplified version you could call it an extension of MATLAB. So here is MATLAB, that's the basic program, then Simulink, then we have the solver, and then we have our model. Now if we run it in an accelerated mode, then we will take the model like this, and this is actually run as a compiled code, and it's communicating on one side with Simulink, and here it can communicate also with MATLAB. If you want to enable this mode, you can use this uh, command, and this will enable the accelerated mode in this way. So we can run it in MATLAB, which is running in background. Now it will not give you any answer if you use the semicolon at the end, so I will just run it without it. We can see that looks like nothing happened, but what will actually happen is that if we now compile the code in Simulink, or if we run it, and if we then go back to the folder where we have it in the folder system, now we will see that this is our model. This is the Simulink model that we're running, and this is my max function, which the Simulink has just created. So it should look like this also in my case. Let's just see if it's true. So I will just run the code and let it compile the model again, and then I will switch to my folder where we should see the result. I will run the model, and we could again see here this scope with the values. It should be the same response like we had last time. Now we have code, you see, optimizing and emitting code completed, and now it will basically run the compiled code. As you see now, this takes definitely much longer to prepare, but for a larger model this might give you an advantage in time for the running of the model. I need to wait until this model is finished. So now, okay, now it gives me some problem. Failed code generation, information file does not exist. So it looks like I am not in the correct folder where I have my Simulink model. At least MATLAB here, you see here now I'm in a different folder. So I will switch to the correct one, which was this one, and now I will run this again, and we'll see if this will still give us a problem. But the problem is that if you compile it like that, then you are not you need to be in the same folder in Simulink and in MATLAB. So now it finished successfully. We can see here the result in the scope, and in my MATLAB folder, well, now this is the scope opening, so this is the response to the step function. So it's still the same model, and now we can scroll through this folder, and this is my model, and this was the accelerated version of the model that I was just running. So let's see step by step how to work in real time. So far this is not real time at all. So the accelerated mode can still have some drops, as we might notice here in this recall from the oscilloscope. Again, you would see this in the lab. You can see that there is a small drop here, and probably here where the computer was doing something, and then there is a small drop over there where this was a similar case. But so the accelerated mode is definitely better than the normal mode, which was doing this. We had larger time intervals where we had problems. So we have improved that response, but this is still not real time. Now, what does it mean if you want to run the code in real time? So remember this picture. Here we have MATLAB, and here we have Simulink. Now, if we are not running in real time, it looks like this. My model and my solver runs as a code directly in Simulink. But if I now want to run it in real time, what we need to do is to take all this, the model, the solver, and run this as a, maybe I could call it standalone process that runs at a very different level. So we'll run MATLAB and Simulink on the PC, but this will run as an individual process with a different priority. And here is how it typically looks like if you are talking about priorities. So here with the green circle, that's the priority for applications. So this is where you have email, where you have Word, Excel, and so on and so on. Lower priorities are assigned, you can see, for device drivers. So they have higher priorities. If they need it, they are assigned the time to do the code. And the highest priority, the most privileged one, is for the kernel, which is the core of the operating system. And the operating system has control over all those higher layers. So it has control about drivers, about applications. If we want to have real-time control, we need to execute the code in the same priority as the kernel. So it will basically run with the same priority as the operating system. Hence, it will not be interrupted by other applications. And if the hardware is fast enough, we can run it in real time because we have a defined behavior with regards to sampling frequency. So now the following commands that you will see will switch the Simulink into this mode, where it will first compile the model, and then it will start it in this kernel mode, and it will communicate through this what's called external mode with MATLAB. So the external mode allows us to communicate between Simulink block diagram and the standalone program. And the standalone program is what we will have as our model. Now it looks like it's really complicated, but fortunately it is not, because there are only a few commands that you need to run in Simulink to do this. And if you are in this real-time mode, your function communicates directly with Simulink, so you can still see the data that you have in Simulink in a chart, but this runs as a standalone, maybe I could call it package of the model and of the solver for the mathematics and of the drivers that do the I/O access to the inputs and outputs. So how to do it in Simulink? Now we need to change the mode to external, and we also need to select the hardware implementation where this will be actually implemented. So let's first take a look on the hardware implementation, which will be in this model settings. So let's first go to model settings, because here we need to select for which hardware this will be actually compiled. So now I need to wait again for MATLAB before it opens this this configuration panel. Note that I still have fixed time here and I have sampling time TS. And in the hardware implementation, we see that right now I'm compiling this. But now I'm wondering why it's grayed out. C code Intel, but I cannot change anything. That's very strange. Strange. Let me try again. Now okay. So now I can select for what device I actually am compiling this. So right now we're doing Intel, at least I am doing Intel. Maybe that's the problem, because I'm not even sure if I have Intel or AMD. I don't know right now. But let's say Intel, and here what kind of operating system do I have? In case you want a different CPU, then for example you see here STM Microelectronics. That's the one that we have on the board, on the development board that we've been working last week. So in the future, when we will be compiling this for the board, we will have to select here the STM Microelectronics board. Okay, so now let's keep this Intel here, and I need another command that will configure this to run in real time, and this command needs to be run again in MATLAB. So the command name is this one. It's configuring the module, and here we have the name of the system. So in my case here I have called that XXX. So my command will be with the XXX. So here I need to do this configuration like that. Já mám cvičení, jo? So here we'll run this. And now I have another problem, because I have kept spaces in my path to MATLAB. So now I don't think I will be able to run this in my computer. So it looks like it's not very successful, this the class today. Was someone able to run it? Or let me ask it otherwise. Does someone see here something else than those three columns?
No, only the same three: normal, accelerator, and the rapid accelerator.
Yeah. That's I don't know why. What's the problem? That's the problem of a different version of MATLAB. Because here I have prepared this in 2019, and now 2020 is not giving me those options. But at least let me show you what we should see. And until next time, I will prepare this for 2020. I have also uploaded the Simulink models in Moodle, so you can try it yourself and see if it works for you. The only thing that you need to modify in the diagrams is that you need to replace the analog inputs here, analog outputs, but basically remove the analog output, and the analog input will be replaced by the signal generator, and then it should run. What I was trying to show you is to show you the execution time that we need to run this model. And there is a block that is called execution time, and that's available in the Simulink desktop real-time library here. So should be I don't see it. Let's go search for it. So I did not see it. So execution time here, and you can actually drag it to your model, and you can if you open the parameters, you can configure to measure the execution times of the task as well as the program. So this will give you two signals, and now you can connect two scopes to your Simulink, to your block. So here you can see the task execution time and the model execution time, and this will tell you how fast is the model able to run on your computer, or how fast is it executed. And the result why I wanted to show you was this one. Here, this is the same model as we have in the Simulink. This is the signal that is now, in this case, it was not simulated. It was a real signal coming from a signal generator from the analog input. And you can see that here we have a nice response of my model. Here when it drops, I have a nice response like that. And this is the execution time, and I believe this is this scope 2 is the task execution time. They're basically about the same, because this model now runs the model runs as a single task, and you can see how fast it is. So this is 2.4 times 10 to the power of minus 5. So basically it's changing a little bit from about 1.6 to about 2.4. So but still, if my sampling period is smaller than let's say this value, let's say 2.5, then it means that this computer is still able to run the real-time model fast enough. And now this is what we would see on the oscilloscope. So the blue is the response of the system, of the computer that runs now the real-time model of the plant, and the yellow signal is a signal from a signal generator generating the step signal for the transient. Okay, so I believe we will finish right now.